Kieran Sweetman.
And I'm Tommy Shapiro, and this is our digital final project. We built a automated payload truck stop that allows the truck to pull up, measure its weight, see its weight, the difference, and then the gate won't open until the truck has met the target weight. These were supposed to act as our scales, but due to some difficulties, we could not get them working. So in the meantime, this potentiometer will represent the weight for the truck load. Changing the potentiometer will change the current weight of the truck. So as of now, say the truck's at 146 pounds, the target weight's at 100 pounds. The difference between the target weight and the current weight will be sent to this Arduino using these communication wires. And then this Arduino will display the difference in the current weight to the target weight, and this acts as our gate. So currently the gate is closed, but as the truck removes weight from its payload and gets below 100 pounds, then the gate will open up. So first we'll discuss the failure in our strain gauge system. The strain gauge system was supposed to act as the scale for the truck to send the weight measurement of the truck to our Arduino. We had a lot of issues trying to get this system working, and the last things that we did to attempt to get this working was we set up these 4 strain gauge systems in a Wheatstone bridge formation. So there's a 1 kilo ohm resistor on each end of the strain gauge, with the red wire being the wire that sits in between the two. So the black and red wires of each of these strain gauge systems are hooked up in a Wheatstone bridge formation, with the red wires all being sent to our load cell amplifier. Our load cell amplifier was supposed to send a 24-bit digital binary number to our Arduino representing the weight, but for some reason that binary number that was being sent was never stabilizing onto a certain value. It was kind of all over the place, from a -100 value to a 2000 value without anything changing on the strain gauge. We tested with our digital multimeter the resistance values at the corners of each of these strain gauges to ensure that the resistance values were matching up to what we expected when there was a strain on the system. And we also tested with the DMM that power was getting to everywhere in our system. After we confirmed that the resistance values were what we expected and that the entire system was getting power, we thought the system would work, but it still didn't, so we decided to move on to the potentiometer to get the project finished. In order to get the rest of our project working, we needed a weight reading. So in order to get a weight reading, we just used a potentiometer due to the failure of the strain gauges. So as you change the potentiometer value, the current weight reading changes. In order to do this, we sent 5 volts from the top to the bottom of the potentiometer, with this communication line being sent to an analog input on the Arduino. So as you change the potentiometer, the Arduino is getting a voltage reading from 0 to 5 volts. And then in the code for this project, we set 5 volt reading to be equal to 199 pounds and a 0 volt reading to be equal to 90 pounds about. So that's how we bypass the strain gauge failure in order to get a weight reading for the rest of our system to work. The next part of our project was to get a display working so that the truck driver could see the target weight and the current weight of the system. To do that, we have this potentiometer to adjust the resolution of the display, and all of these cables are communicating information on what to display onto the LCD screen. We first have the target pounds, and 100 will always be there. That's coded into the LCD to just stay. So the current pounds is also coded to stay there, and then the signal from the code representing the weight from the potentiometer reading is sent to these last 3 places on the LCD screen to show the driver what the current weight of the system is as it changes. The next part of our project was to get 2 Arduinos to be able to communicate with each other. We were running out of digital outputs on our first Arduino, and we needed a lot more, so we decided to get a second Arduino. In order for these Arduinos to communicate, they use digital inputs 0 and 1, which act as receive and transmit communication ports respectively. So if you can connect digital input 0, which is the receive input, to digital input 1 on the other Arduino, and digital input 0 on this Arduino to digital input 1 on this Arduino, as well as connecting the grounds together, then they are now set up to efficiently communicate with each other. This was our master Arduino. So our master Arduino was sending information to our slave Arduino, and our slave Arduino was using that information to compute the necessary actions for its circuit. So our master Arduino first took the current weight and the target weight and took the difference between the two. If the difference between the two was less than 0, then the difference was just 0. And then in the code, it would begin writing to our serial monitor the difference between the two weights. And then the serial monitor, what was written on the serial monitor, so the weight difference, was then sent through the communication wires to the other Arduino, where the other Arduino would then read the weight difference off of the serial monitor port. And once the weight difference was read off of the serial monitor port, it could then do its necessary functions to make the microserver and the displays work. Now that the slave Arduino has the information about the difference between the target weight and the current weight, it can send information to the 7-segment displays representing the difference between the current weight and the target weight. So the 7-segment displays let the truck driver know how much weight they need to lose before the gate will open for them. So as you can see on the right, if the difference is 58, then the signal will be sent to the slave Arduino saying that the difference is 58. The code in the slave Arduino then takes that number and breaks it into a least significant bit and a most significant bit. So it's going to have a 5 and an 8. The 5 will be sent in a binary coded decimal form to the 7447 7-segment display decoder, which will decode that information and update the information to the 7-segment display. As well as the slave Arduino will also take the least significant bit information, which is now 9 because it changed a little bit, and will put that in a binary coded decimal form, send that to the 7447 decoder, which will then decode that information, putting it onto the 7-segment display as necessary. So this does use digital input and output to the decoders in order to properly get the display functioning to the numbers that we want them to show. The last part of our project is the servo motor part of our project, which acts as the gate for the truck stop. Once the gate falls below the target weight of 100 pounds, then the gate will open up, allowing the truck driver to pass. Then the next truck will pull back up, overweight, and the gate will close so that that truck driver cannot pass until its target weight, its current weight is underneath the target weight. The servo motor works by, once the slave Arduino receives the weight difference of the current weight and the target weight, if that current weight is 0, if that difference is 0, then it uses pulse width modulation to send a signal to the servo motor, enabling it to open up. And if that signal is above 0, then it sends a pulse width modulation signal to the servo motor, telling it to go back to its closed position.
And here are our sources.